Next problem is assume that 0 less than epsilon less than 2 to the power minus 22. So epsilon is a very small number. Then it's asking you that if the Gaussian algorithm without pivoting is used to solve the system, the following system, on the Mark 32 machine, then what will be the solution vector x1 comma x2? So you can see the similar example in video lecture 10. Okay, so where we have discussed the case of failure of Gaussian algorithm. Okay, right, similar example has been done there. So we have this we are going to solve this system. So the system is here, that is epsilon 2 1 minus 1. So the system is given. So if you apply the basic Gauss elimination algorithm, so the first step is to create 0 below epsilon, right? So you are going to create 0 below here epsilon. If you look at the first column, you are going to create a 0 by using basic Gauss elimination algorithm. So for doing the same, you are performing the following step. So R2 is changed into R2 minus 1 by epsilon R1. Then reduced system. So then in this case, reduced system will be given by this. So you apply this elementary row operation, then you will obtain the following reduced system. Then this is now in upper triangular case, right? This is a special case where the matrix A is now upper triangular, and now for solving this system we are using backward substitution method. So if you use the backward substitution method, so that will give you the x2 value is equals to minus 1 minus 4 epsilon inverse divided by minus 1 minus 2 epsilon inverse, that is equals to 1 plus 4 epsilon inverse divided by 1 plus 2 epsilon inverse, as it is given that epsilon is greater than 0, however it is very small. So my epsilon is a large number, is a very huge number. So then when you perform in the similar manner in the Mark 32 machine, this is the machine will return you in approximately 4 epsilon inverse divided by 2 epsilon inverse. So that is equals to 2. The value of x2 will be given as 2. Okay, now use this value x2 for getting x1 from the first equation. So first equation is epsilon x1 plus 2x2 is equals to 4. But once you replace x2 by 2, this will give you x1 is, this implies x1 is 0. Right, since epsilon is strictly greater than 0. So you have the solution vector is 0 comma 2 for the, but if you use the basic Gauss elimination algorithm on a Mark 32 machine. Next problem, so that's problem number 7. So the first statement is a definition of a tridiagonal matrix. So when you will say a matrix is tridiagonal, if you have the if it satisfies the following condition, that Aij equals to 0 if mod of I minus j is greater than equals to 2. Then, so if you wish to look at an example of a tridiagonal matrix, here it is given in the below. Okay, so if you look at, so here 3 cross 3 matrix. Okay, so tridiagonal means 3 diagonals will be there. So one diagonal is just below the main diagonal and another diagonal is above the main diagonal. So you have, and the main diagonal is sandwiched in between them. Okay, so then other entries are 0. So if you look at the condition, okay, then further you have been asked to write an algorithm to solve such a system. Then further apply the same. So we are going to apply the same algorithm on solving the following system. So the algorithm which we are going to develop is called Thomas algorithm. Okay, so this problem is actually give you the Thomas algorithm for solving tridiagonal system. Okay, that algorithm is called Thomas algorithm in many textbooks. Okay, right. Okay, so it's given that for a so we know that for a tridiagonal matrix Aij equals to 0 for all mod I minus j greater than equals to 2, and you have the system is like Ax equals to b. So this is the system here. Okay, so x is an unknown vector, and b is a constant vector. Okay, now how this A will looks like for a n cross n matrix. Okay, so if I wish to write A, so I wish to write the entries of tridiagonals. So that this is going to be D1, let's say this is C1, then 0 0 0. Then you have here another diagonal below the principal diagonal, main diagonal A1, D2, C2. Okay, and so on. You are going to be having here last Cn minus 1. You have this is Dn, and here you will have A2 and so on. This is An. And below and Ai's and Ci's are 0. Above Ci's are 0 and below Ai's are 0. So this such type of matrix is called a tridiagonal matrix. Okay, so you can see there are 3 diagonals. Okay, that's a one diagonal, this is second diagonal, and this is a third diagonal. Okay, so to start with deriving the Thomas algorithm for solving such a system, we are pre-assuming that determinant of AKs are non-zero. What is AK? AK is denotes the principal leading minor of order K. Okay, means AKs are invertible. We are trying to make sure that in the entire process the pivot element will not be 0. Okay, and or basic Gauss elimination algorithm will not be failing. Okay, right. So now if you apply, so this is an idea. So you are going to apply the basic Gauss elimination. Okay, create zeros. Okay, so you are going to create zeros or instead of these AIs here. Okay, so for this, what is your step 1? If I wish to write the step 1, okay, so here that R2 is changed into R2 minus A1 by D1 R1. Okay, so then this parallelly D2 is updated by D2 minus A1 by D1 times C1, and B2 is also updated by B2 minus A1 by D1 times B1. So in the first step you are going to perform this. So once you apply this step, you are going to create 0 here. Once you have the updated value of B2, then you are going to create 0 below D2. So what will be the second step here to create zeros there? So here is the, so once you have updated one, okay, so you are going to with R3 is changed into R3 minus A2 by D2 times R2, and then similarly D3 is updated by D3 minus A2 by D2 C2, and B3 is updated by this B3 minus A2 by D2 times B2. So if you apply n steps in similar manner, okay, so means if I wish to write in general, means if you perform ith step, okay, so if I wish to write ith step, you are going to be di's are updated. So I am going to write di's are updated by di minus ai minus 1 divided by di minus 1 ci minus 1, and di's are updated by di minus ai minus 1 divided by di minus 1 ci minus 1, Okay, right, means you are saying the operation is Ri change into Ri minus Ai minus 1 divided by Di minus 1 time Ri minus 1. So this operation you are performing. Okay, for I greater than equals to 2. So 2 less than equals to I less than equals to n. Okay, so n steps you are going to be follow, and then you are going to create zeros. Okay, right. So if I wish to write what is happening, what is the updated system now, so if you look at this process clearly, okay, if you look at this process clearly, the CIs are unchanged, remains unchanged. Okay, so there will be no change in CIs. So after first step, D2 is updated, C2 will remain unchanged, and so on. Okay, A2 is also created 0 here, and D3 is updated. So let's say by using second row, D3 star, C3 remains unchanged, and so on 0. So what you will have is here is Dn star. After n step, you have this is Cn minus 1 and x1 to xn. So in the B vector, B1 remains unchanged. Other things are updated. So other entries are updated. B2 star and so on, Bn star. Now this is so here the zeros here. So upper triangular system, which you can solve by using backward substitution method. So you use the backward substitution method to solve. So if you perform the backward substitution method, so from the last equation, what you will get, xn is equals to bn star by dn star. So to start with, you require this, and then it's a backward substitution. So find xn minus 1, that is equals to bn minus 1 star minus cn minus 1 xn divide by dn minus 1 star, right? So now then n minus 2, xn minus 2 is equals to bn minus 2 star minus Cn minus 2 times xn minus 1 divided by dn minus 2 star, and so on. Okay, and so on. So you can put them in a loop. So what will be the pseudo code for this is as follows. So you are supposed to find, you are supposed to get from user the following input. So you require AIs, BIs, CIs and DIs, all three diagonals and the constant vector. Then you have the following n steps. So for I equals to 2 to n, DIs and VIs are updated. Then you are going to use the backward substitution method for the same. Okay, for finding the final solution. So this algorithm is called Thomas algorithm. Right. Okay, so right. So let's solve the given example. Okay, the example is given. Yes. Okay, this is the matrix. This is tridiagonal system we have to solve. To solve this, though, we have the following. First step means we are going to create zeros below 5. So you need only to create 0 instead of minus 1, because already tridiagonal system. So R2 is changed into R2 plus 1 by 5 R1. So once you perform this, the reduced system. So reduced system will be given by this. So if you are going to the above step, so first row remain as it is, second rows are updated value, third row remain unchanged. So 0 minus 5. So only updated value is D2 star, right? D2. So D2 is only updated and B2 is updated. So this is updated value and this is an also updated value in the stack. Other things are remains unchanged. So if you apply this, you are going to find D2 is updated value is 24 by 5 and B2 value is 19 by 5. Now what is your next job is, you are supposed to now create 0 below 24 by 5. So to do so, you are going to use D2, the second rule. So for doing, we are having the following step: R3 change into, so you have R3 plus 5 by 24 R2. So if you are going to do so, you are going to create 0 here, and where you will get the update, you will get the update instead of here, and you will get the updated values here. Okay, so if you do further, if you apply this, you will get is the following are now new updated values here: D3 star and B3 star. Now apply backward substitution method to find the solution. So if you apply from the last equation, will give you x3 equals to 1. Okay, second last equation, if you solve and use the value of x3, that is 1, it will also imply x2 equals to 1. Similarly, from the first now then use x2 to get one from the first equation. That also will give you x1 equals to 1. So the solution vector is 1, 1, 1 for the given problem. Okay, right. Okay, so now the next problem is, you are supposed to prove that for any vector norm and its subordinate matrix norm. So if you recall, the subordinate matrix norm is given below. So norm of A is equals to supremum over norm AX, such that x belongs to Rn and x is unit vector. Okay, so this norm can be any norm on Euclidean space Rn. Okay, so you have already seen that for the subordinate matrix norm, you have already seen norm of AX is less than equals to norm A times norm X for all X, but since norm X is 1, this is equals to norm A. So what it is asking you, that you also prove that for any vector norm and its subordinate matrix norm, and for any n cross n matrix A, we will always be able to find a non-zero vector X. Okay, you will always be able to find a non-zero vector X such that you actually achieve the equality. Okay, not neither less than equal to. Okay, right. So now, if you recall, okay, let's consider S is equals to, let S is equals to the set X belongs to Rn such that norm of X is 1. So it's a subset of Rn. Okay, so clearly S is closed and bounded. So it's a bounded, okay, and it's closed. Every sequence has a limit, and that limit is in S. Okay, so if you recall, this is then also clear. S is closed and bounded. So if a set is closed and bounded for a finite dimensional space, then it is compact. Okay, and so if you have a continuous function on a compact set, then it always attains its bounds on the same set. You can easily verify that norm is a continuous function. So if I wish to give you the hint for this, you can call, you have, this is mod of norm of xn minus norm of x is less than equals to norm of xn minus x. Since this converges to 0 as n tends to infinity, so you can use this, okay, you can use this fact. The mod of norm of xn minus norm x is less than equals to norm xn minus x, and since if xn converges to x, then norm xn converges to norm x. So this establishes the continuity for the norm function. It's also continuous on the compact set. So this attains its bounds on x. So you will be able to find an x such that norm x equals to 1 and norm ax equals to norm a into norm b. Okay, so attain its bounds on. So this result is true for this. Okay, so the next problem is, do the subordinate matrix norm satisfies the following: norm of AB is equals to norm of BA, B times A, whether this is true or not. Okay, the answer is no. So for an example, you can consider the following matrices: A is equals to 0 1 1 1 and B is equals to 1 2 3 4. Then you calculate AB, okay, the A, and calculate B into A, and then find the infinity norm, find their infinity norm. Okay, and you recall the infinity norm of the matrix, if you recall from the lectures, okay, that is nothing but the maximum over row sum, say the one norm of the row vector, maximum over one norm of the row vector. Okay, right. So if you calculate the infinity norm for AB and BA, which are as follows. So first row sum is in magnitude is 7, and another the second row sum in magnitude is 10, so maximum is 10. Similarly for norm for BA, the infinity norm is, the first is maximum over 5 and 11 it will come, and that is going to be equals to 11. Okay, so this inequalities always remain true, that norm AB is less than equals to norm A into norm B for subordinate matrix norm, right? Okay, so now the next example is using the infinity matrix norm, compute the condition number of the matrix. So for the condition number, if you recall the definition, the condition number is equals to norm A into norm of A inverse. So you require to find the infinity using the infinity matrix norm. So we are going to denote by K infinity of A, that's equals to norm A infinity times norm A inverse infinity. So if you recall again the infinity norm of the matrix, what you will get? So now norm A infinity is straightforward, okay, that is going to be maximum over the element in first row in magnitude 7 plus 8 is 50. The second row sum in magnitude is 19, so that is equals to 19. So infinity norm of the matrix is 19. Okay, right. For the inverse, so if you recall what is A is 7, 8, 9, 10. So if you try to find the A inverse is equals to, okay, so A inverse equals to, okay, 1 upon determinant of the matrix, that is 70 minus 72, that is minus 2. Okay, that is this is 10, this is 7, this is minus 8, this is minus 9. Okay, yeah, okay. So now this is equals to 1 by 2 inside, that is equals to minus 5, 4, 9 by 2, you have this is 7 by 2 with minus. So from here now you can find no inverse matrix infinity norm, that is equals to maximum of the sum of first row is in magnitude is 5 plus 4. The second row sum in magnitude is 9 by 2 plus 7 by 2, that is 16 by 2, and that is 8. So that is equals to 9. So therefore the infinity matrix, the condition number with infinity matrix norm is equals to 9 into 19, that is equals to 171. Right. Okay. So next problem is here. So for any real number p is greater than or equals to 1, the formula defines a norm. Okay, that you can verify. Okay, from your linear algebra. Okay, right. Prove that for each x in R, this limit it actually goes to the infinity norm. So this actually explains why the infinity is used. So how this norm of x infinity is defined? So if you recall, what is norm x infinity? Norm x infinity is maximum over 1 less than equals to j less than equals to n, or let's say I less than equals 1 less than equals to I less than equals to n mod of xi. Okay, let this is equals to xj, mod xj, for some j. Okay, for some j. This is a finite set, so definitely it will be existing. Okay, right. Now you see what is norm of x to the power p? To the power p is equals to summation I is equals to 1 to n mod xi to the power p. But you know, norm of x infinity is equals to mod of xj. What does that mean? This implies mod of xi is less than equals to mod xj. Okay, this implies mod xi is less than equals to mod xj for all xi. So this implies less than equals to, this is less than equals to mod xi is less than equals to mod xs if you perform the sum. So mod xi is p is greater than equals to 1. So mod xi to the power p is less than equals to mod xj to the power p. So you have n time mod of xj to the power p. So this implies norm of xp is less than equals to n to the power 1 by p time mod xj, that is equals to n to the power 1 by p time norm x infinity. Right? So this implies this relation is true now. This implies norm of xp. So what this give you? This implies norm of xp is less than equals to n to the power 1 by p time norm x infinity. Right? Now norm of x infinity is equals to mod xj. Right? Okay. Which is certainly less than equals to, so this is equals to mod xj to the power p to the power 1 by p. Right? Which is certainly less than equals to mod xj mod xj to the power p plus summation I equals to 1 to n I naught equals to j mod of xi to the power p to the power 1 by p. This is true, right? So what is this inside is norm x. This is nothing but p norm of x. Okay, so what does this imply? This implies, so from above to what you will have, norm x infinity is less than equals to norm x p less than equals to n to the power 1 by p time norm of x infinity. Now if you recall limit p tends to infinity, you can prove that n to the power 1 by p is equals to 1. So okay, so this you can prove, okay, by using log both side, and you can do it. Okay, right. So if you have this exercise, so if you letting p tends to infinity, if you let p tends to infinity by using sandwich theorem, so this will imply, sandwich theorem implies limit p tends to infinity, norm of x p is equals to infinity norm, right? This is our claim, right? So now we are going to establish the problem number 12. Okay, so a part is already solved during the video lectures. So second part we are going to look at. Okay, so in the second part, what is it tells you is k of a is equals to supremum over, so we are going to see this part here. K of a is equals to, so first is b, so a and c part both are solved. So we are going to solve the part b, that k of a is equals to supremum over norm of x is equals to norm of y time over the set norm ax by norm of ay. Okay, so we are going to prove this. Okay, now supremum over norm of x is equals to norm of y, norm of ax divided by norm of ay. So you are only talking where x, y norms are equal. Okay, so this set and the set where both are equal and equals to 1, both are the same thing. Norm x equals to norm of y is equals to 1. These both things are same, norm ax by norm of ay. That can be done because you can replace x by norm x and y by norm y. Okay, so this both sets are, this both supremum will be equal, that you can verify. Now this is equal to, so I have, this is supremum over norm of x is equals to 1 and supremum over norm of y is equals to 1 over the norm of ax by norm of ay. Right, now note this is equals to, no, see, supremum over norm x equals to 1 is independent of supremum over norm y equals to 1, right? So you have here supremum norm x equals to 1, norm ax is norm a. So this is equals to norm a time supremum over norm of y is equals to 1 by norm of ay, since x and y are independent. Okay, right. So now if you use the property, so this is equals to norm a is equals to supremum of norm of y equals to 1 by norm ay is same as 1 upon infimum over norm of y is equals to 1 time norm of ay. that is going to be shown as this is so we are going to show this is nothing but norm of A inverse. Okay, the norm of subordinate matrix norm of A inverse. Okay, so now we are claiming, so we are going to claim, okay, so now we are claim, so we are going to claim that norm of A inverse is 1 upon this, norm of A inverse is infimum of norm of y is equals to 1 norm of Ay. If we have done this, then we are through. Okay, right. So now, not that norm of x or norm of y is equals to norm of A inverse Ay. Use the property of subordinate matrix norm. This is equals to norm A inverse times norm of Ay. Okay, so what does this implies? This implies that norm of A inverse is less than equals to norm of Ay divided by norm y. So those norm y you can this implies norm of A inverse is less than equals to norm Ay for all y with norm of y is equals to 1. Okay, so this certainly implies norm of A inverse is less than equals to norm Ay for all y with norm y equals 1. So certainly it will be bounded below by their infimum set. Okay, so norm of A inverse is less than equals to infimum over norm of y is equals to 1 norm of Ay. So this is done. Okay, now y naught is such that norm of A inverse is equals to norm of A inverse y naught. Okay, and norm of y naught is, let's say, 1. Then if you look at this factor, now norm of A inverse of y naught by norm of A inverse norm, that is equals to norm of A inverse. So this such y naught exist. Why? Because of the previous result that there exists in X such that norm of Ax equals to norm A. Okay, so you will always be able to find a such y naught such that this happens. So norm A inverse equals to norm A inverse y naught with norm y naught is 1. Now if you look at this, so y naught by norm of A inverse, and then you take the A inverse over it. Okay, so A inverse y naught is norm A inverse, and now this is this, so you can also verify. Okay, so you can verify the following. So you can verify that norm of A inverse of y naught by norm of A inverse is equals to 1. Okay, norm of A inverse of y naught by norm A inverse is 1. That you can verify. And hence, so once you verify, this is very simple step, verify, because A inverse y naught is norm A inverse using the property of norms, and hence you are able to find. So therefore what you are getting? Therefore there exists a y belongs to Rn norm of y is equals to 1 such that norm of ay is equals to norm of A inverse inverse. So this norm so this certainly implies norm of A inverse is equals to infimum over norm of y is equals to 1 norm of ay, and hence the result holds true. Okay.